Welcome back to our Chem 152 video series. In this video, we'll go over how to find out what reaction is taking place in a galvanic cell and draw a picture. Our problem here asks to find the standard reduction potential of a galvanic cell that consists of a silver plus silver metal half cell and a cadmium 2 plus cadmium metal half cell. We're going to write the balanced reaction and get the reduction potential. The reduction potentials for these reactions that I've given you for silver plus and silver and cadmium 2 plus with cadmium are written on the right. First, a brief introduction to the concept of reduction potential. The reduction potential, or E standard value, is a measure of how much these substances would like to take electrons. Some reduction potentials are positive and others are negative. Positive reduction potential means that that substance would like to take electrons. Negative reduction potential means that it doesn't want to take electrons and is more likely to give them away. In a galvanic cell, what's going to happen is that the substance that wants to take electrons will succeed, and the substance that does not want to take electrons will give them away. If we look to the standard reduction potential values that we've been given with these equations, that's symbolized again by the E standard here, we see that silver has a reduction potential of 0.7996, while cadmium has a reduction potential of negative 0.4030. This means that silver wants to take electrons, and cadmium does not want to take electrons and would rather give them away. In a galvanic cell also, the reaction with a higher reduction potential will happen normally, while a reaction that has the more negative reduction potential will give them away and get reversed. This means that the silver reaction will proceed normally, and the reason for that is because it has the higher reduction potential. However, the cadmium, having the more negative reduction potential, will get reversed. What that also means is that this reaction that's in the literature does not happen. Instead, the opposite happens, and we get cadmium yields cadmium 2 plus 2 electrons. This also means the reduction potential is no longer going to be negative 0.4030. Instead, that will be reversed as well and will become positive 0.4030. The reason why we change the sign is because we reversed the reaction, therefore we also reverse the potential. Notice that once we reverse this reaction, we are no longer having cadmium take electrons, we are now producing electrons with the intention of giving them away. Therefore, to find our E standard of our new reaction, we can say that we have the 0.7996 from silver, and now plus 0.4030 from the reversed version of cadmium. If we add these together, we will get an E standard value of 1.2026. This will be in volts, and this will be our reduction potential for this galvanic cell. However, to write the balanced equation, we're going to have to address an imbalance in the electrons. We might notice our silver reaction has Ag plus 1 electron yields Ag. However, our cadmium reaction has cadmium yields cadmium 2 plus 2 electrons. If we look carefully, we'll see that the first reaction has 1 electron and the second reaction has 2 electrons, and we're going to have to address this imbalance in electrons somehow before our reaction is truly balanced. In order to balance this reaction, we need to try to make the electrons cancel out, and that means we're going to have to multiply both of these equations by something. You may notice in the first equation we have 1 electron, and in the second equation we have 2 electrons, and we'll have to find the least common multiple of those numbers of electrons. Anytime we have an equation with 1 electron and another equation with a different number of electrons, we can just multiply the equation that contains the 1 electron by the other number. So for this equation, we're going to multiply the first equation by 2. Let's write that in. Let's look at what happens when we multiply that top equation by the 2. We'll have 2 pieces of silver plus, 2 electrons yields 2 silver. All of the coefficients get multiplied by 2, and since all of my coefficients were 1, they all become 2. The second equation does not change anymore. It is now cadmium yields cadmium 2 plus 2 electrons. You may notice now that the electrons are now both 2, so they match, and we can cancel them both out. Now that we've canceled out the electrons, let's look on the left side and right side of these arrows. All items to the left side of the arrow become the left side of my new equation. So on the left side of the arrow, I have 2 pieces of Ag plus and 1 piece of cadmium. On the right side of my mark, I have 2 silver with no charge and 1 cadmium 2 plus. This will be my new balanced equation. So now we found both the reduction potential and the balanced equation for the redox reaction to make a galvanic cell. Now we'll draw a picture of that galvanic cell. We'll mark the anode and cathode and eventually the salt bridge and the electron flow. The anode is where the reversed reaction takes place. The reaction that takes place at this anode is going to be our reversed reaction from earlier, and that is cadmium yields cadmium 2 plus 2 electrons. To draw the anode, we'll draw a liquid, and we'll say that that liquid contains cadmium 2 plus, the charged version of the cadmium. And inside of that solution of cadmium 2 plus, we'll put a rod of cadmium metal. We'll label that CD with no charge. We'll then connect that rod to a wire, and that wire will be connected to a voltmeter. That voltmeter is then connected to another wire and connected to another rod, which is connected to the cathode. Now the cathode is going to be where the normally written reaction takes place. The normally written reaction was the silver reaction. We know now that it is 2 pieces of silver plus 2 electrons yields silver. Remembering to write the 2 as the coefficient for all the terms because we had to double the silver reaction to make it balanced. This metal rod will be pure silver solid, and it will be in a solution of silver plus. Make sure that the charge that you write on the solution matches the charge in the equation below. Now, electrons will always flow from the anode to the cathode. We're going to draw an arrow with electrons, and we're going to draw it from the anode, flowing toward the right, toward the cathode. Then to finish our picture, we'll draw the salt bridge. The salt bridge consists of a tube with a porous plug in it, and that tube is going to be connected to both solutions in the anode and the cathode both. Usually inside of this salt bridge will be the solution KNO3 or some similar compound. Whatever it is, it's going to be a salt that is highly soluble. Now, in this salt bridge, what happens is that the KNO3 is going to split into pieces, K plus and NO3 minus, and then the negative piece of that salt, whatever it happens to be, will flow toward the anode. The positive piece of that salt will flow the other direction toward the cathode. To symbolize that, I can show that NO3 will be symbolized by red dots, and will show that most of the NO3 will flow toward the anode, and that most of the potassium, symbolized by these green dots, will flow toward the cathode. One final point here, we're also asked where is the oxidation taking place and where is the reduction taking place. The normally written reaction, that is the cathode, is always going to be the reduction, every time. And this means the anode must be the oxidation. However, you may be asked what is the oxidizing agent and what is the reducing agent. It turns out the reduction is where you'll have the oxidizing agent. So it's a little bit backwards from what you would expect. We say the oxidizing agent will be the silver plus. That means the reducing agent takes place wherever the oxidation does, so again, it's backwards, and it will be the cadmium. This can be a little bit tricky to remember, so just remember wherever the oxidation takes place, that's where the reducing agent is. Wherever the reduction takes place, that's where the oxidizing agent is. Thank you for watching, and we'll see you again soon.